It's got law. It's got legal law. It's got state law. I do. What?
You want to go home?
31.
I didn't insult you. I wanted you to be quiet.
All right, if you guys can turn to page 17. Okay, we did number 1, and we're going to try number 2. Again, if you need scratch sheet, hopefully, with the first problem that you did, there's space on the back. But if you at any time need scratch sheet, I have paper on the top of the shelves that you can grab one. So. Just to recap with number 1, though, we talked about how if you see cosecant or secant, you don't want to think in terms of those functions. Yeah, you want to think in terms of sine and cosine, and just pretend like you're doing a sine or cosine graph, and then at the very end, you can make that that jump to the cosecant or secant graph. And we talked about how with number 1. We treated cosecant like sine, and we just did everything in terms of sine. We found the period the same way as sine, interval, the C value, the B value, and we graphed everything according to how we would do with sine. The only thing that is going to change at the end is you're going to have that midline. You're going to have that dotted sine graph, but we know that's in the background, right? That's not the true graph that we're after, but it provides us a lot of nice boundaries. So if we can get the sine graph, the D value, the vertical asymptotes, then creating the cosecant or secant graph is going to feel like the easiest part of the problem, because you're just graphing those kind of parabolas. And we talked about how after you graph your sine, look to see where it intersects your D value. And that's going to be where you're going to drop your vertical asymptotes. Okay, your asymptotes are not necessarily going to be dropped where it intersects with the x-axis, especially if there's a vertical shift up or down. But once you have your sine graph, your D value, and your vertical line, then you're just looking at the peaks and valleys of your sine graph, and then you're just sketching parabolas that jump off of those points, and you're just creating kind of like a reflection version of the dotted line that you have in the graph. Okay, so number 2, y equals negative 0.5 secant of 2 theta minus pi plus 3. We're just going to pretend like we're working with what? Good, cosine. Yeah, so cosecant is you'll do sine for cosecant, but for secant, you'll do cosine. So go through the process. You're going to rewrite your function, right? You're going to pull that B value out and adjust your phase shift. Okay, so go through your steps. I will show the work after you guys have a chance to progress. Scratch sheet. Thanks. Yes. just to make sure that we're on the right track, we're going to just pretend like we're doing everything from a cosine perspective. We got to pull that 2 out in front. And because of that 2 that comes out, we know we got to make an adjustment with that pi. And we're always going to be counterbalancing what we see out there. So if we see a 2 in the top, we got to balance it with the 2 in the denominator. And once you make that adjustment, then everything should be clear in terms of your A value, your B value, your C value, your D value. Okay. Take your B value, find your period, from your period, find your interval. We're moving to the right, pi over 2. We see a minus pi over 2. We know we're going to add pi over 2 or 2 pi over 4 to every one of our initial x values. Especially if you want to match common denominators, you can also use your calculator to just add those fractions. Once you have everything in place, then you're really just targeting your top row and your bottom row. Make sure you have your D value dotted line +3, because that dotted line is going to help you figure out where those asymptotes are going to be dropped. It's going to be where your cosine dotted graph is going to intersect with your D value dotted line. And then you can create vertical lines that drop down. And if you can see the cosine graph, if you can see that vertical line, then you're just plopping your asymptotes, your parabolas. And that's the true graph. That you'll put in a solid line, because that's the only graph that is technically there, right? All the dotted lines are kind of in the background to help us shape our graph. Okay, any questions with these order pairs? Show the graph in a minute, but want to make sure that you guys are seeing everything that you want to see here. Yes, when you're graphing your sine or cosine, make sure you use dotted lines, because otherwise I'm going to treat that like part of the graph. That's really not part of the graph. So use dotted lines and use very faint lines so that I'm. Creating it. Show me that this is really cool. Yeah, so. Yes, yeah, that's right. It's solid line, that looks like a little bit cosine graph and. This one. Still trying to figure out, but I think we'll have a couple things to get that. So. Yeah, guys, our calendar is a little bit in flux. We'll see. Yeah, I think we'll probably do the check-in quiz on Thursday instead. Okay, but let me show the graph. Okay, so we have all these order pairs here. We have first order pair at pi over 2 and 2.5. Now I made my graph really close together. You can space it out a little bit more if you want to get more of that cosine graph so that it doesn't look as small as mine. But I'm just plotting my cosine graph that's been shifted, moved, and stretched, or sorry, condensed. And I know that my asymptotes are going to be dropped where the intersection of the cosine and the d values, right? So my d value is +3. Okay. And technically, if I'm just graphing one period, then I'm going to, you see how at pi over 2, there's not an asymptote there, and I'm only going to show 1/2 of my downward parabola. But here in the middle portion, I'm going to be able to create my full parabola because it's sitting between the asymptotes. But this one to the right, I'm only going to create this part. Now, it looks kind of strange here, but this is technically one full period if we're starting from pi over 2, because after this, our graph is going to begin to repeat itself, right? Yes.
How do you know like when to put the full parabola up or down?
Up or down? Good question. So the way you know is however the graph looks, okay, think of it as a reflecting off of the peak and the valley. So if the cosine graph has a valley, then you're going to create a parabola that kind of bounces off of that point. So basically, you're just creating kind of like a reflection version of what you see. So if I see a peak for my cosine graph, then I'm going to create a secant or cosecant graph that bounces off of the peak. Yeah. So it's always going to, so you're always going to have these parabolas or these parabolic shapes kind of meet. And you know, if there's a maximum for a peak for a cosine, then you're going to create a minimum for your Yes.
The original like.
Yeah, so you're going to fill those in with the exact same information as the cosine. So your cosine, vertical stretch, period, phase shift, vertical shift, it's the same. Your secant is going to be the same as your cosine. So everything you gather from your cosine is going to still stand, right? So vertical stretch, we can say compressed by 1/2. For period, we can say pi. For phase shift, we can say to the right, pi over 2. For vertical shift, we can say up 3. Right? So everything that you gather from cosine in terms of transformation is going to apply for your secant. Okay, any questions there? Okay, let's just do writing equation of the function described. So if you can turn to page 19, let's just go down. And anytime we see secant and cosecant, we just want to think in terms of sine and cosine, right? And just gather everything from that perspective, because we can, everything for secant is going to correspond with cosine. So number 9, again, we're on page 19 here. Secant function vertically stretched to be 5 times taller than normal. Horizontally compressed to have a period 1/2 the length as normal. Shifted pi over 4 units to the right and 10 units down. So let's just pretend like we're dealing with a cosine function and gather everything like we normally would. Okay. So so if you want to do this in terms of cosines, just so that you can have something more familiar to work with, more than welcome to, and then just change it at the end to secant, or you can think in terms of secant and go from there. So but right now I'm going to say cosine because I think we're comfortable with sine and cosine. We've been doing all our work in terms of sine and cosine. Okay, vertically stretched to be 5 times taller than normal. So what does that mean? A equals 5. Okay. Horizontally compressed to have a period 1/2 the length as normal. So what's 1/2 of normal? It's pi, right? Because normally cosine is 2 pi. So if I want only half that period, then my period is pi. And then from here, how can I get to my b value? Yeah, so I have my formula, right? 2 pi over b. Okay. So basically, you're doing everything like cosine, and the only change is that you're calling it secant at the end. Shifted pi over 4 units to the right. So what's our c value going to be? Minus, yeah. And 10 units down. D equals -7. So not much different than cosine. You guys want to try number 10 and 11? For number 10, cosecant function. So just think in terms of what? Pretend like you're doing sine. Yep. So pretend like you're doing sine, treat it like sine, but then at the very end, just call it cosecant. Okay, try 10, try 11. It should feel like how you've been doing it on the quiz, or just calling it the reciprocal function, but ultimately, it's going to feel like as if you're doing sine or cosine. Okay, check your answers, and we're going to move into the last two trig functions, right? We've done sine and cosine, we've done cosecant and secant, and now the final two are cotangent and tangent. And cotangent and tangent are a little different from these other four, but they're similar to each other. So, but a lot of information in terms of the period, the interval, the A value, the B value, C value, it's all going to be similar, but there's going to be some distinct differences with cotangent and tangent compared to the other four. Okay, so we're going to turn to page 20. Okay, I'll come back to this page for those of you who are still on number 10 or starting 11. Okay. All right, so here's page 20. Exploring the cotangent and tangent graphs. Okay, so we'll start with cotangent. Cotangent is, I guess, a little bit easier because it doesn't feel like it's cut off like how we're going to see with the tangent. So we're gonna, it's not gonna feel cut off like how we saw with the secant graph. Cotangent. Right now, just like how when we started cosine and sine, we did all the middle values, but we're gonna have a much more efficient way. We're gonna have that kind of 5 number system where we can just graph the most important parts and everything else will fall in line. But let's just think in terms of unit circle. How do we find cotangents if you're looking at a unit circle? X over y, right? And we talked about how you can just cover up the denominator. X over y is a lot easier because you can just don't worry about fractions. So, cotangent of pi over 3 will just be 1 over root 3, right? And we're just going to go down those values and practice. And yeah, so exactly right. So cotangent is x over y, and so x over y. What's 0 going to be here? X over y, which is undefined. Okay, so I want to make sure that we understand that it's undefined, which means that we're going to be expecting some vertical asymptotes, just like with secant and cosecant. Okay, pi over 6, we have x over y. So again, I'm just going to cover up the denominator. It just makes it easier for me to divide because they're just going to cancel each other out. So root 3 over 1, which is root 3. What's pi over 4 going to be? Over root 2, which is just what? Just 1. Okay. Pi over 3, 1 over root 3. Don't have to worry about rationalizing because eventually we're going to convert all these to decimals. Okay, pi over 2. What's x over y going to be? 0. Yep, 0 over 1 is 0. Okay, just going down the line, right? Negative 1 over root 3. Negative 1. Pi is also undefined, right? X over y. Okay, after this, things will just kind of repeat itself. So I'm just going to just fill this in here. Okay, decimal value, you can use your calculator or you can just watch me convert them with what I've already gathered. After this, everything just kind of repeats itself. Okay, so let's get a picture of our cotangent graph. Let's do the easy parts first, all the undefined. And it looks like it's landing right at 0, pi. So we'll go up to 2 pi, but then after that, we can just create repeats as well. So we can see that pattern showing up. I'm just going to label pi over 2, all the middle ones. You just kind of follow, go from one to the next. Okay, so let's go ahead and plot these order pairs here. We see there's a vertical asymptote at 0, but then at pi over 6, we're going to go up to 1.73. That's the first tick mark. Halfway between 1 and 2. Sorry, halfway between 1.5 and 2. 1, pi over 4. 0.57, that's between 0 and 1. And then pi over 2 is 0. Negative 0.57 is next. Negative 1, negative 1.73. After this, it's going to repeat itself. So fill those in. Okay. We kind of can imagine how these graphs will look. They will just kind of create this downward slope of a curve. And we can pretty much imagine how these others will look, right? So there's your cotangent graph. It's a little simpler than the sine and cosine, right? It doesn't go up and down. It just falls in the same direction, right? It's just kind of downward slope all the way through. Okay. There's something a little different though in terms of the period. What do you think the period is for this cotangent graph? Just pi. Why is it not 2 pi? Right. It's already a complete repeat after pi, right? I know that with secant and cosecant, we kind of saw similarities, right? The parabola is opening up, then it's opening down, but then we don't consider the opening down as the same as open up. So that's why secant and cosecant has 2 pi, because it needs to go through kind of that 2 parabola behavior before it repeats itself. But here, this is a complete repeat after pi. So that's something that's different with cotangent and tangent, is that your normal period is going to be half the length of your other trig functions. It's only going to take pi before it completes its cycle. Domain. So domain, we would say it's all real numbers, except we got to worry about the pi. And this is similar to what we saw with cosecant, right? That we have to kind of have a rule to name all these vertical asymptotes. So similarly, we're going to say all real numbers, except 0, pi, 2 pi. So the way you want to say it is, we want to say 0 plus, and how can I reach my next vertical asymptote? Pi, and then I want to include what? Pi n. Yep. So that just indicates, okay, that's going to give me a rule, so I can keep going and find all the other ones if I wanted to. So plus pi n plus 1 pi, 2 pi, 3 pi, 4 pi. We can also let that n go in a negative direction. They can be any integer. So we can say where n is an element of an integer. So we don't want n to be just any number. We want it to be either a positive or negative integer. We don't want it to be like 0.1 or 0.6 because then it's not going to land at the asymptote that we care about. Okay, range. What do you think range is? Right, there's no break, right? It's not like the cosecant and secant where we have to do -infinity to 1 to -1 and then from 1 to infinity. Here, there are no breaks at all. And it's also not like sine and cosine where it's just jumping between -1 and 1. It covers all real numbers. So you can say all real numbers. You can write that notation, or you can write it like interval notation. Either one's fine. They both mean all real numbers. Yes.
How would you write the domain in?
It'll be, yeah, for interval notation, yeah, we're not gonna, I don't think there's a way to write interval notation. We have to kind of give it that kind of awkward, writing it out like, 0 plus pi n. Yeah. Okay. All right, so let's look at number 1. And I think there should be enough room. Okay, there should be enough room. We're going to create a table just like how we would with sine and cosine. We're going to do a 5-number system, but I'm going to kind of tell you what that's going to look like for your initial. Okay, but let's see if we can gather some information here. What's our A value for our cotangent? It's 5. Okay. Do we have a B value? No B value. Do we have a C value? Good. So no C value either, because there's no parentheses. So if we see any number hanging out there, we just have to assume that it's not part of theta. It's by itself. So B is just 1. So if you don't see it, if you don't see a B value, it's always just going to be 1. C is 0, and then D is -1. So there's no phase shift. It does go down by 1. There is a vertical stretch, but there's no horizontal vertical compression. It's going to stay as the parent graph. Okay. So here's our formula. Our formula for cotangent and tangent is going to be a little bit different. If you had to guess, what do you think the period formula for cotangent is? Good. Pi over b. Why is it pi over b and not 2 pi over b? Because the pi is the parent period. Yeah. So everything else, all the other trig functions, all the other 4 trig functions we've done so far has been period of 2 pi. So that's why we do 2 pi over b for every one of them, except for tangent and cotangent. I know we haven't done tangent yet, but it's going to feel very similar. You see that it's going to start repeating itself after pi, so that's why it's only pi over b. Okay. Is the period going to change if I were to plug in b into my formula? No. So my period is pi. Okay, so period is pi. Vertical stretch pi. Period is pi. Thank you. Your interval will be the same formula. So your interval is the same across all your trig functions. Your interval is p over 4. So what's my interval going to be? 5 over 4. Okay, so here's our theta, cotangent theta, 5 cotangent theta. Create a table just like how you normally would. And guess where we start? 0. Yep. So 0. Pi over 4. Pi over 2. All right, this is plus 1/4 is 1/4, 2/4, 3/4, and that's 4/4 or pi. Now, the second row we haven't talked about, right? We know the pattern for sine, we know the pattern for cosine, we know what cosecant is, we just copy sine, we know what secant is, we just copy cosine. But now we have a different set of parent behavior for the y value. Okay, so this is how it's going to work. Your first and last are not going to be ordered pairs. They're going to be vertical asymptotes. So you're going to say VA. So your asymptotes are going to hug your graph on either side. Okay, so VA on both sides. Your cotangent is going to be decreasing. Okay, your cotangent is a decreasing graph. If you had to guess, tangent is going to be a what? Increasing. Yeah, so that's really the only difference. Cotangent is going to be decreasing. Tangent is going to be increasing. And then they're going to be misaligned a little bit. But if you can keep that in mind, then you're going to have a lot of similarities that you're going to see between cotangent and tangent. Okay, it's going to be a decreasing graph. And it's going to be easy numbers. We just know that these numbers are going to be decreasing. So it's going to be 1, 0. Guess what the next number is? -1. That's it. So it's still a 5 quote unquote number system. But just know that it's going to vertical asymptote on both sides and really only just the numbers 1, 0, -1. Okay. All right, so multiply 5 to every one of these numbers. These will stay as what? Vertical asymptotes, right? That's not going to change. You're not going to change that by multiplying 5. Here you go, 5, 0, -5. And that's it. Plot the points, and the graph should show up nicely.
Correct, -1.
Oh, sorry, I forgot about that. My bad. D is -1, right? Thank you. So 5 minus 1 is 4. Sorry, I should have started with 1 without the vertical shift so that you can get a better picture. But I think we can do it. 0 minus 1 is -1. -5 minus 1 is -6. Okay, so our D value is -1. We can create that graph. Sorry if you're running out of room. But it's not too much, so I think we can do it. Okay, so okay, I'm gonna create all my x values here. So 0, pi over 4, pi over 2, 3 pi over 4, and pi. And I'm gonna have asymptotes on both sides of my interval here. I can create my D value at -1. This is quote unquote the center of my cotangent graph. And just plot your points. So at pi over 4, we're going to go up to 4. At pi over 2, we're going to be at our center at -1. And then at 3 pi over 4, we're going to go all the way down to -6. Running out of room here, I'm not able to quite show, but basically you want your graph to basically connect in a way where it's going to get closer towards the asymptote on both sides, but no, my graph is a little bit short. I'm not able to quite get that far, but you get the idea. It's going to, as it goes towards infinity, it's going to kind of gravitate towards asymptotes on both sides. Yeah. Okay, any questions here? Okay, with the remaining time, I want to see if I can get started with the tangent graph so that you can maybe see it. We'll finish it off tomorrow, but let's just see if we can get a taste of the tangent graph. I'm going to skip all these middle order pairs and just get to the most important points. So if you guys can do this, tangent, we know tangent is going to be y over x. I'm going to skip all the decimals here. So, but we're going to get a lot of the same behavior. We're still going to get vertical asymptote, but it's going to be a little bit offset from what we experienced with tangent. We started with cotangent because it just looks a little cleaner. Tangent looks like it's been cut off midway, and then you're finishing off later what that graph looks like. Okay, but the difference here is that there are still asymptotes. The period is still pi, but instead of 0 and pi and 2 pi, now it's pi over 2, 3 pi over 2. So your asymptote is going to be a little bit off-centered from your cotangent. Sorry if you guys are copying that down. Okay, so go ahead and label your pi over 2, 3 pi over 2, 5 pi over 2. And go ahead and drop asymptotes along those values. Not at pi, okay? At all the fractional major values. So instead of 1, 0, -1, what do you think tangent is going to look like? -1, 0, 1. So it's going to be rising instead of falling. So, and it's going to, and the full graph is going to show between pi over 2 and 3 pi over 2. So go ahead and at pi over 4, go ahead and plot -1, 0. So if I want to see the full period, I have to start at pi over 2 and end at 3 pi over 2. But this distance is still what? It's still pi, right? Because pi over 2 plus pi gives me 3 pi over 2. But if I were to just look at the graph between 0 and pi, it's going to look a little bit like it got cut off. So let me kind of show you what that looks like. If I want to go from 0 to pi, it'll look like this. It'll look like I started halfway and I got cut off and then I finished it up, rather than this. Your tangent graph looks a little bit strange just because it looks like, you know, I'm seeing two halves of the same graph. You know, I can get the full graph if I start at pi over 2, but if I'm showing from 0 to pi, it's not going to look as clean, quote unquote clean, as cotangent. Okay, so we can finish off the rest of the graph here. Just make them all go from -1, 0, 1. Okay, I think we're gonna be able to finish off tangent tomorrow. We'll do a review. And I think we're gonna do a check-in quiz on Thursday. Again, it's just gonna be most likely 2 problems, and we'll be able to spend our first half of class reviewing and then second half of class taking it.
Sorry.
Yeah, my graph is wrong. Let's just start here. Yeah.
So it's a test on Friday.
No, it's gonna be next week sometime.
Okay.
Yeah. Like,
I did not have a service.
You still trying to find out?
I'm sorry, I did not have a service.
You're also.
Are these free? Some are these free training your day after college.
Yeah.